Vehicles in marine, air, and unmanned applications utilize line of sight or LOS guidance laws to execute a wide range of motion control scenarios, including tracking objects and paths, as well as following and maneuvering paths. The purpose of this presentation is to introduce an adaptive line of sight guidance law or ALOS guidance law for marine and aircrafts, and it is in reference to ALOS guidance law for path following of air and marine craft by Thor Eifossen. The focus of this study involves a system of the following control equations A and B, where y dot subscript e superscript p is the rate of change of the cross-track error, visualized in Figure 1 as a perpendicular deviated distance from the intended path between points x sub I, y sub I, and x sub I plus 1, y sub I plus 1, all superscript n, and psi sub d is a heading autopilot yaw angle command, which is a control command directed to the autopilot system to maintain or adjust the craft's position by yaw. The Crab angle is beta sub c, which is mathematically defined as the inverse tangent of v over u, where u and v respectively denote the surge and sway velocities, and is used as a measure of the angle of a vehicle's heading relative to its actual track, and thus is highly representative of the disturbance effects of wind and currents. While control strategies have previously assumed that theta 1 equals theta 2 equals 0, or that theta 1 can be designed to cancel the Crab angle, the focus of this study highlights a control strategy that aims to cancel the Crab angle by testing an adaptive law for theta 2 and comparing its effectiveness and disturbance matching relative to other control systems at canceling the Crab angle, which thus drives the cross-track error to 0 and hence improves the accuracy of the vehicle's pathing. Note that the following summarization of various control methods will frequently refer to thetas 1 and 2 from equation B. All of the guidance laws to be discussed are line-of-sight guidance laws, which are named so due to their dependence on a direct line of sight between the vehicle and its target to obtain visual information that is fed back through a control loop to make adjustments as needed. The various line-of-sight guidance methods tested include ALOS adaptive line of sight, proportional line of sight, ILOS integral line of sight, which utilizes a classical and adaptive approach, and ELOS extended state observer line of sight. All of these guidance methods abide by different stability criteria, which are highlighted below in Table 1 and have their respective proofs in the article. There is a visual aid on the right that can be referred back to later in the article when discussing pitch, yaw, surge, roll, sway, and heave, which can affect the stability of each system. The first of these laws to be discussed is the ALOS guidance law, which is a guidance method proposed by Foster in this article. Gamma is the adaptation gain, and beta is a parameter estimate. The integral state, which is the integral-based parameter in the system, such as those that depend on Ki, predicts the Crab angle, which is further visualized in Figure 2. The difference between ILOS methods, which are to be discussed later, and ALOS methods are that the ALOS predicts the Crab angle, while ILOS uses saturating arctangent functions to compensate for the Crab angle. This is best performed at constant speed in a straight line for the ALOS system. The proportional line of sight guidance law, on the other hand, heavily depends on the proportional state as seen in equation 5, where Kp is defined as 1 over delta, and delta is the look-ahead distance. The proportional guidance law, psi sub d, emulates the heading angle command of an experienced sailor to account for error caused by perturbations. It utilizes a vector field surrounding its travel path to determine its pathing. It has been widely used and demonstrates many forms of stability, but does not always converge when exposed to the drift forces caused by wind, waves, and currents. It also lacks the ability to counteract error in under-actuated vehicles, and these issues can lead to large cross-track errors during path following. However, the following ILOS system has improved upon these issues. The nonlinear ILOS integral line of sight guidance law, where theta 1 is not equal to 0 and theta 2 is equal to 0, has a classical and adaptive approach. The classical approach uses a yaw angle in equation 1 to drive the cross-track error to 0 and thus improve accuracy of pathing, while the adaptive approach replaces equation 6 with parameter estimate 8 and is better with non-constant additive disturbances such as wind, which can change very dynamically. It has shown better control than proportional line of sight response to drift forces, and additionally, it provides an alternative in path following accuracy to under-actuated vehicles, which are unable to produce their own sway forces for counteraction. It has shown success in multiple applications in linear and curved path following, as shown in the hyperlinked article by Kahariha. Extended State Observer Line of Sight, or ELOS guidance law, estimates time-varying Crab angle with equation 11. It is proven to be ISS, or input-to-state stable, meaning that it asymptotically approaches stability despite the effects of a specific set of bounded external disturbances and control inputs, such as, for example, a known limited range of potential input commands and current or wave disturbance effects. It assumes the following listed conditions and has performed well both at estimating crab angle in rapidly varying conditions in application, as seen in the hyperlinked article by Liu, and later on in the case study. In this case study, a robust model of the Remus 100 Autonomous Underwater Vehicle, or AUV, was used to test its efficiency and robustness in response to a stochastic or arbitrary ocean current when controlled by the proposed ALOS guidance law relative to pre-existing guidance laws of classical ILOS and ELOS. Note that because ALOS outperformed adaptive ILOS in terms of an adaptive control approach to crab angle estimation on the following computer simulation, adaptive ILOS was not tested on the AUV model itself. The following parameters were chosen for the physical testing. Delta equals 10 meters, ILOS integrator gain of K equals 0.1, ALOS adaptation gain of gamma equals 0.0006, ELOS gain of K equals 0.5, an initial current speed of V sub c equals 1 meter per second with direction beta V sub c of 180 degrees, and a sampling time of 20 Hz. Before the case study on the Remus model, computer simulation was performed on both ILOS strategies as well as ELOS and the proposed ALOS guidance laws in response to time variable crab angle. All systems performed well with a small magnitude of rate of change of crab angle. While classical ILOS demonstrated high overshoot in terms of cross-track error, followed by the proposed ALOS, with adaptive ILOS and, as anticipated, ELOS showing minimal error. ALOS and ELOS, however, best predicted the crab angle, presenting an advantage for the prospective ALOS guidance law. The goal of the tested line-of-sight guidance laws was to follow a set of 6 defined waypoints in the stochastic ocean current with minimal cross-track error and accurate crab angle estimation. The testing was performed in 2 phases. In Phase 1, from 0 to 900 seconds, the purpose was to simulate relatively standard operating conditions. The AUV accelerated up to its cruise speed while exposed to an ocean current with constant magnitude and direction. The current increased the vehicle's speed during the first phase, as shown in Figure 5. The sideslip angle, synonymous to crab angle, beta, changed slowly while traveling through the desired waypoints in Phase 1, as shown in Figure 8. Note the vehicle depth, roll angle, pitch angle, and yaw angle of the AUV during testing, as shown in Figure 7. Phase 2, however, after 900 seconds, presented an extreme stochastic current, with the current's direction changing from 180 to negative 180 degrees in just 1 minute. Simultaneously, the magnitude of the current was increased from 1 to 2 meters per second. This phase tested the guidance law's cross-tracking error and crab angle estimation abilities in the worst-case scenario conditions. The performance of all 3 LOS guidance laws is similar in Phase 1, with successful tracking obtained for each algorithm. The proposed ALOS did outperform ELOS in this case in terms of sideslip angle estimation, while ILOS maintained the best cross-track error. In Phase 2, ELOS, as anticipated, presented the best cross-track error performance. However, the prospective ALOS guidance law outperformed both ILOS and ELOS in terms of crab angle tracking, for which ILOS was previously the most accurate option. ALOS and ILOS showed lower overshoot than ELOS in terms of cross-track error, and ALOS demonstrated better error than ILOS in Phase 2. The significance of these findings is that the proposed adaptive line-of-sight guidance law presents a promising, unprecedented level of accuracy in terms of crab angle estimation when exposed to dynamic disturbances such as wind, waves, and ocean currents in combination with relatively fast cross-track error convergence. While its performance in terms of crab angle estimation is only slightly better than that of its ILOS predecessor, it demonstrates a much faster convergence in terms of cross-track error. This convergence can be especially important in many applications that require intense levels of accuracy, such as docking and missiles, where accuracy is of the utmost importance. ELOS does still present a better cross-track error performance than any other LOS guidance system currently, but with further suggested testing, such as variable plans and alternative testing conditions, the combined high level of crab angle estimation accuracy brought forth by ALOS and cross-track error convergence of ELOS can be taken advantage of, providing a foresight of never-before-seen accuracy in path following for marine and air autonomous vehicles.